In this video, we will be going through factors which affect rate of reaction, how we can measure reaction rate, and then discuss collision theory. Here are our syllabus dot points. First, we'll begin by asking the question, what is reaction rate? Reaction rate pretty much describes how fast a reaction can occur. We can also say that reaction rate is how fast a product is formed from the reaction, or how fast the reactant is depleted from the reaction. On the table, we can see that the products formed is on the y-axis, and the time is on the x-axis. The blue reaction demonstrates a faster reaction because more product is formed in a shorter period of time. Thus, the red reaction is a slower reaction because less product is produced compared to the blue line in the same amount of time. There are a few ways in which reaction rate can be determined. We mostly utilize the y-axis of the graph to determine these parameters, and this can include the volume of the gas that's produced, any changes that occur with color, or changes in temperature. Examples of reactions that produce gas include combustion reactions, acid and metal carbonate reactions, and metal and water reactions. In the setup which is demonstrated here, we have a syringe that's connected by a gas delivery tube to a conical flask, which acts as a reaction vessel for a reaction which produces gas. When the gas is produced, the pressure will cause the syringe to push out, and the marked lines will indicate how much volume of gas has been produced. We can also monitor color changes by using a spectrometer in a process that is called colorimetry. The colorimeter device is a device which measures the absorbance of particular wavelengths using the color of the solution, hence the name, and thus it can help to distinguish between different concentrations. Here we have multiple solutions of different concentrations, and they are going to provide different absorbances in the spectrometer which we are using. Change in temperature can be measured as reactions all either absorb or release energy. So if we are absorbing energy from the surroundings, then the temperature of the surrounding is going to decrease. If we're releasing energy, then there's going to be an increase in temperature in the surroundings. And a reaction is going to be completed when the change in temperature completely stops. So what we see to the right-hand side is a table that shows the change in temperature of a reaction that releases energy. We can see that we are measuring an increase in temperature over a period of 30 seconds. Some factors which affect a reaction rate include the concentration of reactants, the pressure and volume, temperature, surface area of reactant, and catalyst. Collision theory is an idea that states that chemical reactions are the result of collisions which happen between molecules or atoms, and so the reaction rate is going to depend on a few different factors. The first factor is the rate of collision between molecules. The second factor is the activation energy of the reaction, and the third one is the molecular orientation of molecules. We will go through one by one what each of these mean. The rate of collision is the frequency at which the molecules collide into one another. If I have a greater rate of collision, it means that there is going to be a greater reaction rate. Let's look at this animation on the right-hand side. What we see is that there are many different molecules of varying sizes and speeds that collide into one another. The rate of collision, thus, is how often these collisions are occurring between the molecules. And so in general, as I said earlier, a greater rate of collision leads to a greater reaction rate. While rate of collision is a factor that affects the rate of reaction, the rate of collision itself is also affected by multiple factors. They include concentration, pressure, temperature, and surface area. If concentration of reactant is higher, that means that there are more particles moving around in the given volume, which increases the frequency at which the particles collide. And that applies to molecules in both the aqueous and gaseous state. So if we look here, imagine these were moving around. The amount of times that these would collide into each other would be much lower than for this one, which is the same volume with a higher concentration. An increase in pressure has the same effect as a reduction in volume, because it increases the rate of collision. Again, this applies to gaseous molecules because they occupy the greatest volume. When we have a decreased volume, we should remember that to calculate concentration, we use the formula N over V, where V is the volume and N is the number of particles or moles. In this case, we have the same number of particles, but because the volume is decreasing with an increase in pressure, what's happening is therefore C is going to be increasing in total. Temperature also affects the rate of collision, as temperature determines the amount of kinetic energy that exists in the system. So the higher the temperature, the greater the kinetic energy of the system. And so if there's more kinetic energy, that means that more collisions will occur, and also they will occur faster, increasing the reaction rate. The opposite is true for lower temperatures. When the temperature of a system decreases, the kinetic energy within that system will also decrease. When the temperature of a system decreases, the kinetic energy within that system also decreases, leading to fewer collisions. And thus we get a slower reaction rate. This applies to molecules in all states. An increase in the surface area of a reactant is going to mean more particles are exposed to the other reactant. As a result, there is a greater chance for particles to collide into one another, and with more successful collisions, we are going to have an increase in the rate of reaction. So for example, if I grind metal into a powder, we are going to be increasing the surface area. If we look at this diagram, both this one on the left-hand side and on the right-hand side have a total of 8 cubes which make it up. The surface area of this one, however, is going to be much smaller because if we look at this block, for example, the particles are only able to collide against these 3 surfaces. Whereas if we split it up, it is now able to have twice as much coverage around all sides of that block. Here is an example question. So we consider this reaction between magnesium and hydrochloric acid. It produces magnesium chloride and hydrogen gas. The question asks us to use collision theory to answer why filing magnesium into a powder will increase the rate of reaction. Well, we know that if we grind down magnesium, which is a metal, we will vastly increase the surface area of the reactant despite not changing its volume. So for us to answer this question, we would start off by saying that filing leads to an increase in surface area, and so by collision theory, the number of collisions will increase, and so therefore, rate of reaction will also increase. So recap on the factors which affect collision rate. They include concentration, pressure and volume, temperature, and surface area of reactant. We just looked at factors which affect collision rate, which itself is one of the factors which affect reaction rate. The second factor which affects the reaction rate is the activation energy of the reaction. So collision theory states that a collision between molecules will only result in a chemical reaction if the molecules have sufficient energy. So if they collide but they do not have enough energy, then they do not react. This required energy is also called the activation energy. The reason why it's so important to understand how all these factors work together is because collision theory states that an increase in collision rate will not matter if the molecules themselves don't have enough energy to react. So looking at these two profile diagrams, they demonstrate to us that the reaction on the left has a smaller activation energy, which is the difference in energy between the reactant and its peak, than the one on the right-hand side, which has a larger activation energy relative to the left-hand one. The Maxwell-Boltzmann distribution is a distribution of energy amongst molecules that are in a system. On this distribution curve, only the molecules which exist to the right of this activation energy are molecules which are going to react upon collision. The effect of temperature on reaction rate is that since we increase the temperature, there is a greater amount of kinetic energy which exists within that system. The red line on this Maxwell-Boltzmann distribution indicates the reaction energy when the temperature has been increased. Since there is an increase in the kinetic energy, we can see that there are more molecules now which overcome the activation energy. Originally, as shown by the black line, only this number of molecules were going to react. Now it has increased to this total amount of molecules which are reacting. Thus, increasing the kinetic energy means that they collide with more energy, and so more molecules are going to meet the activation energy. As a result, we have more collisions occurring, and thus we have an increased reaction rate. In the opposite scenario, we're decreasing the temperature of the system. This means that we are going to have less kinetic energy overall, and so now fewer molecules are able to meet the activation energy. The collisions are less likely to result in a reaction, and so we have a decrease in reaction rate. The addition of a catalyst is going to reduce the activation energy by providing an alternate reaction pathway. Unlike with temperature change, the average energy of the molecules does not change. But more molecules now have enough energy to react since the requirement is lowered. So activation energy went from this section where only this amount of molecules were able to react. Now, after the catalyst has been added, the activation energy has gone down, and now this number of molecules are able to react. Thus, we have the same effect as an increase in temperature with an increased reaction rate. This example asks us to use collision theory to explain the effect of an increase in temperature on the rate of reaction. First, we know an increase in temperature is going to lead to an increase in overall kinetic energy of a system. This means that the molecules will have more energy and will collide more frequently. This increase in kinetic energy means that more collisions will overcome the activation energy. And activation energy is simply described by this EA, and therefore increase in reaction rate. Our next example asks to compare the effects of using a catalyst and an increase in temperature on the rate of reaction. So both of the catalyst and increase in temperature will have the same effect of increasing reaction rate. However, the mechanisms by which they do this are different. Using a catalyst provides an alternate pathway, which lowers the activation energy. An increase in temperature allows it to overcome activation energy. The final factor which affects collision theory is the molecular orientation. Molecular orientation refers to the orientation of molecules during the collision. For example, here we have the collision between carbon monoxide and oxygen gas to produce carbon dioxide and an extra oxygen. In this reaction, when the carbon monoxide and oxygen gas collide with the oxygen ends facing, there is no reaction that occurs. The reaction can only occur if oxygen has access to the carbon side of the molecule. It is important to note that this is uncontrolled, meaning that it is unaffected by all factors of concentration, temperature, pressure, volume, or surface area. To summarize, the rate of reaction, as per collision theory, is determined by three factors: the collision rate, the activation energy, and the molecular orientation.